안녕하세요. 한양대 박사과정 왕자님입니다. 제가 오늘 Exploring Explainability with OISE algorithm에 대해 좀 영어로 설명하고 발표하겠습니다. With the development of artificial intelligence technology, the machine learning models are becoming more and more complex, and the accuracy of the model is improved, but the interpretability of the model, that's transparency, is getting lower and lower. The decision-making process is largely unclear, and it's difficult to explain to users. So the XAI algorithm we will introduce today provides a new technique that takes images as input and output class probabilities, resulting in a salience map indicating the importance of each pixel to model predictions. It detects the model and obtains the corresponding output by using the masked version of the input image, thereby estimating the importance based on the experience. However, in some methods, the interpretability is required through the deformation and integration of white box model, and the use of the specific network architecture is restricted. So instead of white box-based approach that use gradients or other internal network states to estimate pixel importance, the techniques that utilize the black box model are proposed. So we propose a new technique, OISE, optimized input sampling explanation with a salience map based on the black box model. The pixel importance is obtained by feeding a masked version of the image into the model, and which is then visualized to obtain the salience map. These are the characteristics of the technology. It's considered as a complete black box model, and it can generate an importance map for any network without accessing its interior and doesn't need to be re-implemented for each network architecture. And it can create a mask in an optimized way, optimize the loss function, and constantly update the mask to generate a minimum mask area and affect the decision score. So this is a specific implementation method. First, input the image I and initialize a random mask, optimize the MSE loss function using gradient descent technologies, and select the initialized parameter value, for example, theta equals to 0, 0, 0. Then we choose a step size 0.1, calculate the partial derivative from the loss function, update theta until theta converges, and add L2 regularization to make many parameters close to 0 but not 0. By reducing the parameter size, the complexity can be reduced, and the decision score can be affected by reducing the mask area. And then update the mask M according to the optimized loss function and use it to cover the input image I. And multiply the input image I by the mask M, input the image covered by the mask into the base model F, and output the weights. So F is a black box model that produces a scalar confidence score for a given input of Y. The final salience map is a linear combination of masks where the weights are derived from the scores of the target classes corresponding to the respective mask inputs. And finally, we can obtain the salience map by making the mask weights. So this is a comparison between this technology and previous technology, CAM and gray CAM. We can see that this technology has higher accuracy and has greatly improved the accuracy of the recognition range. This is the result obtained by inputting the image into the algorithm. It can be seen from the figures that the model explains well why these objects are recognized as a tench, terrapin, steel drum, geometry, vulture, and unicycle. And there are two types of optimistic evaluation metrics can be applied here, namely deletion and insertion. The deletion will change the decision-making of the underlying model, and the more important pixels are removed from the image, the lower the probability of predicting categories where the importance of pixel is defined by the significance score. The sharp decline in lower areas on the probability curve indicate a good explanation. On the other hand, the insertion metric adopts a complementary approach, and as more and more pixels are introduced, the increase in measurement probability shows a better explanation. When deleting the pixel from an image, the pixel value can be set to 0 or other values. The same applies when inserting pixel. According to the figure on the right, as more and more pixels are introduced, the higher AUC indicates a better explanation. There are several methods to remove pixels from the image, such as setting pixel values to 0 or other in constant grayscale value to blur pixels. And the same applies when introducing pixels, such as starting from a highly blurred image and gradually eliminating the blurring of the region. So OISE is a new black box interpretation model for the better visual interpretation. By optimizing the loss function and constantly updating the masks, the computation of randomly generated masks can be reduced, the area of generated masks can be minimized, and the decision score can be influenced. With these methods, the end users can get a better interpretation, and it also provides new ideas and thoughts for future research. It's hoped that more accurate and interpretable algorithms will be created through more in-depth studies in the future. 네, 여기까지입니다. 들어주셔서 감사합니다.